Jayambi, how are you all? I hope you all are good. I welcome you all to my YouTube channel. My name is Prince Ranpara. I'm a PhD scholar in the Department of Chemical Engineering at the Indian Institute of Technology, Ropar. So in today's lecture, we are going to understand the deriving of the design equation of continuously stirred tank reactor by utilizing the concept of the general mole balance equation, right? So in today's lecture, you will understand the continuously stirred tank reactor and you will get all your answer and you will understand the design equations, right? So let's get started. The first question which arises in our mind is, what is CSTR, right? What is continuously stirred tank reactor? How the continuously stirred tank reactor differs from the other all industrial reactors, right? What are the significant importance of CSTR in industries, right? So in today's lecture, you will get all your answers and you will understand, right? So let's get started, right? So first of all, the continuously stirred tank reactor itself, the name suggests, right? The in continuously stirred tank reactor, we have the word reactor, right? So reactor, which means reactor, and tank, which means tank is a vessel, right? So vessel, so let's say the reactor is the enclosed vessel or a tank in which the reaction will take place, right? So entire tank, which means the any vessel, right? Any vessel, it's indicated by the term tank, right? And reactor, reactor means the enclosed vessel in which the reaction will take place. And stirred means by using the stirrer or agitator, we are providing uniformly mixing of the system volume throughout the entire reaction volume, right? And continuous means in the continuously starting reactor, continuous means we are having the continuously inlet molar feed stream to the reactor, right? And we are providing the continuously stirring to the reaction environment, due to which we'll have the uniformly distribution of all the system variables throughout the entire reaction volume, right? And after the completion of the reaction, the products will exit the reactor through the outlet stream indicated by outlet flow rate, right? So in continuously starting reactor, we'll have the continuously, as you can see in the video, right? So we have the continuously a feed stream of inlets, right, which is feeding to the reactor, right? So you can see in the video, we can see we have the continuously feeding of the reactants to the inlet feed stream, right? Inlet molar feed streams. So the reactants are continuously fed to the reactor, right? You can see you can see and understand, you can visualize by understanding the video, right? So we have the in the continuously starting reactor, we have the continuously inlet molar feed stream which is entering to the reactor, right? To the reactor, and in the reaction environment where the reactants will get consumed, will get interact, and will get converted in the new products, right? After the formation of the product, we are providing continuously stirring, right? So the stirrer or agitator is used for mixing the entire reaction volume, right? Due to which we'll have the uniformly distribution of all the system variables, right? And after the reaction, the products are formed. They are the products which will exit through the outlet flow rate, right? Outlet stream, which is FJ, right? You can see in the video, right? So by utilizing the concept of the general mole balance equation, and by utilizing the general mole balance equation, we'll try to derive the design equation of the continuously starting reactor, right? So first of all, we need to understand some conditions, right, by which we can say the continuously starting reactor is an ideal continuously starting reactor, right? Ideal CSTR, right? So okay, so first of all, we need to understand in the ideal continuously starting reactor, we have the continuous inlet feed stream which is feeding to the reactor, and by utilizing of the stirrer or agitator, we are providing a uniformly mixing of entire reaction volume. Okay, so we are continuously stirring in the entire reaction environment, right? And the products are formed, and those products which is formed are continuously exiting through the reactor outlet stream FGN, right? So okay, so in continuous starting reactor, we have the continuous inlet flow rates, continuously reaction will take place, and continuously we have outlet flow rates, outlet molar flow rates, right? So, and by using the stirrer and agitator, we have uniformly mixing, right? Uniformly mixing, which means we have the uniform spatial distribution of entire system variables, right? We have uniform spatial distribution of all system variables, like the temperature, concentration, pressure, catalysis or catalytic activity should be uniform throughout the entire reaction volume, right? So at each and every position and time, we have the same concentration, right? So we are having the perfectly mixing condition, which means the reactor concentration should be equal to the outlet feed concentration, right? The products which are exiting the reactor through the outlet stream, okay, so the concentration of the outlet stream should be equal to the concentration of the reactor, right? Reaction concentration, right? So firstly, the perfect mixing is the reactor concentration should be equal to the outlet concentration, right? And we have the steady state operation. Steady state, which means with respect to time, the overall reactor behavior will be constant, right? So there will be no change in the overall reactor behavior with respect to the time. It's indicated by the steady state, right? And we have the spatial uniform distribution of all the system variables. So temperature, concentration, pressure, catalyst, reaction and rates are uniform throughout the entire reaction volume, right? And we have the constant volumetric flow rates, right? So we have the volumetric flow rate as Fj naught, and we have the volumetric flow rate as Fj, right? So we have constant Fj naught inlet molar flow rates, and we have constant Fj outlet molar flow rates, right? Due to the constant volumetric flow rates of inlet and outlet, we have the uniform constant volume, right? I hope you have understood. Okay, now let's say by utilizing the general mole balance equation, we'll derive the design equation of CSTR, right? So we are writing the general mole balance equation, right? So in minus out plus generation is equal to accumulation, right? So inlet is being identified by Fj naught, right? Fj naught minus outlet is denoted by, represented by Fj, plus generation term is Gj is equal to dnj by dt, right? So we have understood we have derived the general mole balance equation in the previous lectures, right? If you want to recall, I request you to please watch the previous lecture, right? So we have the equation as Fj naught minus Fj plus the generation term can be represented as integration of Rj into dV with respect to the entire reaction volume V, right, is equal to the accumulation term is dnj by dt, right? So we have the general mole balance equation, right? Now we are applying the general mole balance equation to a CSTR, okay, which is operated at a steady state conditions, right? So at the steady state condition, the accumulation term will be equal to 0, right? So due to those reasons, dnj by dt will be equalized to 0, which is indicated by the steady state conditions, right? So let's say in order to understand in detail and in order to make you simplified and make you understand very easily, I will make you understand the comparison between the steady state and the unsteady state, right? So let's say in this portion I have made the comparison of the steady state, okay, steady state operation and the unsteady state operation, right? So let's say in steady state operation we have the accumulation term to be equal to 0, right? And in the unsteady state the accumulation term is not equal to 0, right? So we'll understand how. Okay, so let's say in order to understand, firstly we are understanding the steady state, right, where the accumulation is equal to 0. So how the accumulation term is equal to 0? So let's say we'll understand both the comparison, right? So let's say in our reactor, in our reaction environment, initially we have the presence of 10 molecules, right? 10 molecules of A is present, right? So let's say 10 molecules are initially present inside the reaction environment, right? Now we are using the continuously stirred tank reactor, so we have continuously inlet feed stream, right? And we have continuously outlet feed stream, and we have continuously mixing, right? So with the continuously inlet molar flow rates, the 5 molecules are entering per second to the reactors, right? So 5 molecules are entering through the inlet molar feed stream to the reactor in the reaction environment, right? So now we have 5 molecules present in the reaction environment, right? So out of those 5 molecules, okay, the three molecules interact, react, and they are getting consumed into the new products, right? So the three reactant molecules are getting consumed, are getting reacted inside the reaction environment, and they are getting converted into the new products, right? So due to those reasons, so let's say inlet term is 5, right? The inlet term is 5 molecules, right? Inlet term is 5. So 5 minus, and 3 molecules are consumed, right? And 2 molecules are just exiting the reactor, right, through the outlet stream. Okay, so those 2 molecules out of 5 molecules, 2 molecules are just getting exit through the outlet stream. They are not taking part into the reaction, right? And they are just getting out of they are just leaving the reactor system through the outlet phase stream, right? So we'll apply the general mole balance equation, right? So in general mole balance equation, we have the in minus out plus generation is equal to accumulation, right? So inlet we are having 5 molecules are entering to the reaction environment per seconds, right? So we are writing 5, right? And minus outlet, so outlet means out of 5 molecules, 2 molecules are not taking part into the reaction, and they are just getting out, they are just leaving the reactor system, right, without taking part into the reactor. So due to those reasons, we are 2 molecules, so we are subtracting 2 molecules from the out of 5 molecules, right? So in out we have 2 molecules just exiting the reactor system. In generation term here we'll write as reactants, right? So out of 5 molecules, 3 molecules are getting consumed, so means out of 5, 3 molecules are getting consumed, so we'll subtract, right? Out of 5 molecules, 3 molecules are getting consumed and they are getting converted into the new products, right? So in generation term we'll write minus 3. I hope you have understood why we are writing minus 3, right? So out of 5 molecules, 3 molecules are getting consumed, and they are consumed means minus 3, right? And they are getting converted into new products, right? And new products will form. Okay, so due to those reasons we are writing minus 3. Now if we calculate these, we can see 5 minus 2 minus 3 is equal to 0. Obviously minus 2 and minus 3 is minus 5, so 5 minus 5 is 0, which means accumulation is 0. I hope you have understood, right? Which means there are no chemical species accumulating inside the reaction environment, right? So which satisfy, right? So we have the initially 10 molecules were present inside the reaction environment, and after the inlet feed stream and after the reaction takes place, there are no chemical species accumulating inside the reaction environment. Okay, due to those reasons the accumulation is equal to 0, which implies the steady state condition, which means with respect to time we'll have the 10 molecules were present, right? So with respect to each and every time we'll have the 10 molecules only present inside the reaction environment, right? So let's say, for example, if we analyze the reaction if we analyze the reaction sample, if we analyze the reaction environment, then after 5 minutes we have the 10 molecules present inside the reaction environment. Okay, 10 moles per second, and we are also getting the concentration is same, right? And after, let's say, after 1 month or 2 months, if we analyze the reaction environment, if we are continuously operating the CSTR, right, then after 1 month or 2 months, we will have the same 10 molecules of 10 molecules are present inside the reaction environment, right? So which means there is no change with respect to time, which means steady state, right? So overall behavior of the reactor is constant with respect to the time. Okay, so there are no changes with respect to time, so due to which it implies the steady state operation, right? Steady state condition where accumulation term is equal to 0. I hope you have understood, right? So for the condition we are having the perfectly mixing, and we are operating the CSTR at the steady state operation, right? So due to which the accumulation term will be equalized to 0. I hope you have understood, right? Now in contradictory to the steady state operation, we have the unsteady state operation, right? So in the unsteady state operation, the accumulation will not be equal to 0. Now how the accumulation term will not be equal to 0, we'll understand that, right? So let's say we are taking the same example. Okay, so let's say initially 10 molecules are present inside the reaction environment, right? Now with the inlet feed stream, the 5 molecules are entering at each and every second to the reactor in the reaction environment, right? Now from that 5 molecules which are entering to the reaction environment, to again only one molecule is reacting, is getting interacted, reacted, and that one reactant molecule is getting converted into the products, right? And 2 molecules are unreacted, right? And that 2 molecules out of 5 molecules, the 2 molecules are just exiting the reactor through the outlet stream, right? Outlet stream. So now we'll apply the general mole balance equation, right? Again, so in minus out is equal plus generation is equal to accumulation, right? So in inlet we are having the 5 molecules which are entering per second to the reaction environment, right? So 5 minus outlet means same, the 2 molecules are leaving the reactor system, they are unreacted, right? And they are not taking part into the reaction, and they are just leaving the reaction environment, right? So in the outlet stream we have 2 molecules, right? So 5 minus 2 in generation, which means again we are writing in terms of reactants, right? So let's say out of 5 molecules only one reactant is getting converted into the new products, right? So due to those reasons, we are out of 5 molecules only one reactant is utilized, is consumed, right? So due to those reasons we are writing minus 1, right? So in minus out plus generation, so inlet we have 5 molecules, 2 molecules are just leaving the reactor, so minus 2, and only one molecule is consumed and reacted and have converted into the a new product, right? So minus 1. So if we calculate, so 5 minus 2 minus 1 is minus 2, and minus 1 is minus 3. So 5 minus 3 is plus 2, which means plus 2 molecules are getting accumulated inside the reaction environment, right? So plus 2 molecules per second, right? So plus 2 molecules means 2 molecules each and every second are getting accumulated inside the reaction environment, right? Okay, so accumulation is not equal to 0 in the unsteady state operation, right? I hope you understood, right? So at each and every second, 2 molecules or 2 chemical species, right? 2 molecules of chemical species are getting accumulated inside the reaction environment. Okay, so again recalling, we were having initially 10 molecules which is present into the reaction environment, right? 10 molecules initially, the 10 molecules are present inside the reaction environment. Now with the each and every seconds, right, 2 molecules are just adding up to the reaction environment, right? Because we have understood, right, unsteady state operation, which means at each and every seconds 2 molecules are just accumulating inside the reaction environment, which means in the initial amount the two molecules will add on, right? So after each and every second, let's say at t is equal to 0, we were having initially 10 molecules, and after 1 second now 2 molecules just add up, 2 molecules accumulated inside the reaction environment, right? So after 1 second we'll have the 12 molecules, right? And after 1 second we'll have the again 2 molecules accumulating inside the reaction environment, right? So from 12 will after 1 second we'll have 14 molecules which are accumulating inside the reaction environment, right? And after another 1 second another 2 molecules are accumulating inside the reaction environment, right? So from 14 we'll just add on, so 16, 18. So likewise with respect to time the molecules will increase, right? And accumulation will increase, due to which accumulation term is not equal to 0 in the unsteady state operation, right? So molecules will keep on increasing, right, from initial amount 10 to 12, 14, 16, and so on. With respect to time the accumulation will increase, right? It's called the unsteady state operation, right, where the accumulation is not equal to 0. I hope you understood the comparison between the steady state operation and the unsteady state operation, right? Unsteady state operation, which means overall reactor behavior will change with respect to the time, right? And steady state operation, which means overall reactor behavior will remain constant with respect to time. No changes with respect to time is called the steady state, right? So I hope, so due to those reasons, we are writing the steady, we are having the continuously starting reactor operated at the steady state conditions, due to which the accumulation term will be equalized to 0. I hope you have understood, right? I hope you have understood, right? Now we are having the, so due to those reasons, we can write that dnj by dt is equal to 0, right? So dnj by dt represent the accumulation term, right? So perfectly mixing, which means we have all the system variable are uniformly spatially distributed throughout the entire reaction volume, due to which we have the same concentration of same concentration present at each and every different position and time inside the reaction environment, right? So due to those reasons, the rate of formation or the rate of generation will be constant or will be uniform throughout the entire reaction volume, right? Because we have the perfectly mixing condition, which means we have the uniformly distribution of all the concentration, rate of the reaction, temperature, pressure, catalytic activity throughout the entire reaction volume. Due to those reasons, the rate of generation and the reaction rate and the concentration will be uniformly distributed throughout the entire system. Due to those reasons, the rate of generation and the reaction rate will be uniform and will be constant with respect to the entire volume B. Okay, so due to those reasons, we can write the generation term as V into Rj, right? With respect to the entire reaction volume B, the rate of generation is Rj. Same at each and every position, at each and every time, we have the same rate of generation, we have the same rate of formation, right? So we can modify the integration of Rj into dV to V into Rj, right? I hope you have understood, right? So this equation 4 indicates the ideal CSTR is assumed to be perfectly mixed, right? Now we can apply the equation 3 and 4 to the equation 2, right? So we can write Fj naught minus Fj plus generation term as V into Rj is equal to accumulation term is equal to 0, right? Now we can rearrange the equation 5 and we can write as, so we are taking the V into R, we are making the subject as V into Rj, right? So we are rearranging the equation 5th and we are making the subject as V into Rj, right? So we are transferring the V into Rj to the right hand side. So if we are taking the V into Rj into right hand side, the sign will change. Okay, so from positive sign it will become negative sign, because we are taking the term V into Rj to the right hand side. Okay, so that's why for those reasons we are writing minus Rj into V will be equal to Fj naught minus Fj, right? And in equation 6 we are making the subject as V, volume, right? So volume V is equal to Fj naught minus Fj, and we are dividing by minus Rj to the entire right hand side, right? So V is equal to Fj naught minus Fj divided by minus Rj, right? So here we have derived the design equation of continuously starting reactor, right? So this equation 7 represent the design equation of continuously starting reactor, right? So by understanding the design equation of continuously starting reactor, where we are trying to analyze the reactor volume, which is necessary to reduce the chemical species J from the initial molar flow rate from Fj naught to the outlet molar flow rate, which is final molar flow rate, which is Fj, with respect to the reactants, right? With respect to the rate of reaction, rate of disappearance, right? It's minus Ra, right? So we understood, right? Now the molar flow rate term can also be written as, no, I hope you have understood up to this part, right? Now let's say the molar flow rate can also be written as the product of concentration of species into the volumetric flow rates, right? The molar flow can be written as the product of concentration of species indicated by Cj into volumetric flow rate is indicated by volumetric flow rate V, right? So now we'll write the unit balance, right? We'll try to understand the unit balance. So molar flow rates is indicated by moles per unit time, right? Concentration indicates a concentration unit is mole per unit volume, right? And volumetric flow rates is indicated by volume with respect to time, right? So from the numerator and denominator, volume can be cancelled off, and we have the same units on left hand side and the right hand side. So moles per unit time and moles per unit time, right? So now we are applying the equation 8 at the entrance of the reactor. So at the entrance of the reactor, we are having the inlet molar flow rate indicated by Fj naught, right? So Fj naught can be written as Fj naught is equal to Cj naught into V naught, initial volumetric flow rate, right? So initial molar flow rate is indicated by Fj naught is equal to the initial concentration of chemical species. J is Cj naught into initial volumetric flow rate at the inlet, which is indicated by V naught, right? And at the reactor outlet, right? And at the reactor outlet, we have the outlet molar flow rate is indicated by Fj, right? So at the outlet reactor outlet, we have the Fj, right? Will be which can we can write as the final molar flow rate is indicated by Fj is equal to the final concentration of chemical species J is indicated by Cj into the final volumetric flow rate V, right? So therefore we can use the equation 8 and 9, and we can substitute both the equation 8 and 9 into the equation 7, right? So and we can write in terms of reactant A, right? A, right? So V is equal to Fj naught minus Fj upon minus Rj. So we are writing in terms of volumetric flow rate and concentration of reactants A, right? So V is equal to V is equal to V naught into Ca naught minus V into Ca upon minus Ra, right? So equation 10 represent the ideal CSTR design equation in the form of volumetric flow rates, which is V naught and V, in the form of concentration Ca naught and Ca, and in the form of rate of disappearance, which is indicated by minus Ra, right? So I hope you have understood, right? So in today's lecture, we have derived the design equation of CSTR, and CSTR also plays a very significant importance in all the industrial applications, as we have discussed in the batch reactors, right? In the petrochemicals, in the pharmaceuticals, biotechnologies, at each and every places we are using in order to enhance the product, in order to enhance this yield of the desired product, in order to manufacture the desired product at very large scales, and with the continuous flow, we can scale up the manufacturing of the desired product by utilizing the continuously stirred tank reactor, right? So I hope you understood how we have derived the design equation of continuously stirred tank reactor by utilizing the concept of the general mole balance equation, right? So I hope you all have understood. So I request you all to please make a note, right? Please make a note, right? And if you have any questions or suggestion, please feel free to comment below, right? I will try my best to reply to your comments, right? So in upcoming lectures, we will understand how we will derive the design equation of plug flow reactors, okay, by utilizing the concept of the general mole balance equations, right? So until then, stay focused, keep learning, and stay curious. Thank you for watching my video. Jai Ambe.